I think you can start.
All right. Thank you very much, and thank you for the invitation. I will be talking about an ongoing collaboration with Rafael Madou, also from Laval, Quebec City, Yulia Semyonova from Toronto, and Renming Song from Urbana-Champaign. All right. Let me start with a few general remarks. In what follows, I'll be working in dimension greater, equal, or higher to 3, physical dimension, but in principle, everything that I'll be mentioning, the methods should work in dimension 2 as well. All right, so this is the principal object in this talk, the stochastic differential equation. So a classical and central object. Here, B is a standard Brownian motion in RD. B is a vector field, usually called a drift, which will be in general locally unbounded. And sigma is a measurable matrix of diffusion coefficients. I will be making a few remarks about discontinuous diffusion coefficients, but in most of the talk, I will simply take this matrix to be identity matrix. So the principal object that will interest us is the drift. As you can see, at time t, 0, and the solution, the unknown process, is equal to x, a point that is fixed in space. One of the central problems in probability theory and partial differential equations is the question, what are the minimal assumptions on the drift that ensure the existence and uniqueness of a solution, of a weak solution or a strong solution? So the question of well-posedness of this stochastic differential equation, which is written in this form, beta form, or sometimes is written in a shorter form below. All right, that's the question that will interest us. And speaking of singular drifts, well, the applications come in particular from stochastic optimal control, hydrodynamics. This question is closely related to analogous questions that one can pose for parabolic equations. And in fact, continue with general remarks, one can say that there are two approaches to modeling the process of diffusion. Partial differential equations, parabolic equations, and stochastic differential equations. So the connection between two is, of course, well known and described here in this next few lines. So solution of the Cashew problem for the parabolic equation. As you can see, I'm already taking the diffusion coefficients to be 0. So the operator that interests us is Laplacian, perturbed by drift. So as you can see, a solution to this Cashew problem is expectation of the initial function of the process, where the process is this solution to the stochastic differential equation. As you can see, I have square root of 2 in front of the Brownian motion. This is because I want to have minus Laplacian. If I put Brownian motion, then I would have to put 1/2. All right. Yeah, so this is the relationship, and it goes both ways. One is somewhat more straightforward. If one can solve a stochastic differential equation, then by taking expectation, one obtains a solution to the Cashew problem, and vice versa. If one can solve the PDE in a good way, meaning obtain certain regularity results that I will mention, then this will allow you to solve a stochastic differential equation. I will make this notion of solution more precise in a moment. But this is not surprising that solving SD in a sense requires more information, because one also obtains more information in return. If one in principle can solve the PDE and call it a day and say that, well, here's the description of the diffusion process. But solving the stochastic differential equation allows you to apply powerful machinery, such as Ito's formula and so on. All right, now speaking of the notion of the solution, so there is in most of the talk, I will be talking about martingale solutions. So we will state the level of distributions or probability distributions. Namely, we'll be looking to, we'll be trying to construct probability measures on the canonical space of continuous trajectories. Well, this is in a sense similar to what one does when one is trying to construct Brownian motion, that is to construct Wiener measure. So we'll be doing the same. Now, this notion of the martingale solution is not far from the notion of weak solution, which we can define directly, or simply say that, well, if we have a martingale solution, as you can see, there are three conditions. The first condition says that the process has to start X. In a sense, all the terms well defined. The second condition, the third condition is that, that we have a martingale. This expression gives us a martingale. And if one is taken as the test function, so here are the test functions of complex support, but if one can take as the test function these two functions that are not equal to 0 to infinity, then one can conclude that this martingale, the corresponding martingale is a Brownian motion, and this will give you the SDE. So that's the notion of the solution. Now, after these preliminary remarks, let me start with the first part of this talk, and this will be a counterexample due to Beck, Flandoli, Gubinelli, Murelli, who considered, among other results, many other results, the following stochastic differential equation with the Hardy-type vector field. So, as you can see, well, this Hardy-type vector field, there is a constant C in front of it. We'll be assuming that C is positive. If one takes C equal to 0, then this SDE, this term disappears, and one simply obtains that the solution is the Brownian motion. Brownian motion starting at the origin as a standard Brownian motion. However, if one adds this drift, and as you can see, this drift becomes stronger as one approaches the origin. So it's a radial drift, and it's a radial attracting drift. So it forces the trajectory, it makes it go to the origin. And locally, one expects that the solution, if it exists, should look like a Brownian motion with this drift. Now, as I mentioned, among methods, they prove that if the constant C is sufficiently large, not just sufficiently large, there's a precise value, C is greater than D over 2, D is the dimension, then this stochastic differential equation, well, in a sense, when I'm talking stochastic differential equation, this is always a Cashew problem. So starting at the origin has no weak solution. The attraction to the origin is simply too strong. The trajectory arrives to the origin and stays there, and no longer looks like a Brownian motion. So there is no solution to the to this SDE. Okay, now notice that this vector field is almost in LD space, well, at least locally. But we're interested in local singularities of the vector fields here, in critical local singularities. So this vector field is almost in LD log, and in principle, one can use this example as an argument for the optimality of the class LD. So, meaning there are results, there are positive results concerning B in LD. Well, as you can see here, I wrote B belongs to LP plus L infinity, meaning that B is of the, can be put in the form of a vector field which is with entries in LP plus a vector field with entries in L infinity. But again, in this talk, the behavior at infinity, we will ignore that. One can even, for the purposes of this talk, one can assume that B is of complex support. By the way, I don't have clock near me, so please let me know when I have when I run out of time.
Sure.
Okay. Thank you. All right. So here are the positive results, and I will mention a few names. There are many others who should be mentioned here. So, if one is looking for an LP condition on the drift, then P equal to D is the best one can hope for. The reason for this P equal to D is, well, it's easy to see it if one is looking at the corresponding parabolic equation. So the scaling is, or for instance, is looking at the scaling. So if P is strictly greater than D, then zooming in in a sense, improves the coefficients. When p is equal to d, then zooming in doesn't do anything. When p is less than d, well, there are a few results that are known, but well, many things break down. All right, and so as I mentioned, this example of such a vector field, when c is greater than d over 2, the constant can be used as an argument for the optimality of the class LD. But as I will try to convince you, the situation with this counterexample is a lot more interesting. So there are two questions that I will pose here, and I will try to answer. The first question is LD is it the right condition for studying weak well-posedness of the SDEs? So existence of weak solution, existence and uniqueness, or the existence and uniqueness of martingale solution. Surprisingly, a more general L2 condition on B. So I will specify what I mean by that in a moment, but let's say L2 condition on the vector field called form boundedness is sufficient to guarantee well-posedness, weak well-posedness, weak existence, uniqueness, well, some uniqueness, I should add. We'll not be talking about uniqueness in law, but something weaker and fairer. And when we go back to this counterexample, so we know that when C is strictly greater than D over 2, then there is no weak solution. What about C less or equal than D over 2? The attraction to the origin is, well, rather not so strong. Does a weak solution exist? And we will see that yes, and we will get this existence results for the entire class of form-bounded vector fields that will contain LD. All right, so that's the first part of my talk, the George's method in LP. That will more or less allow us to prove the positive result for the counterexample and really show that this is a counterexample what we saw. Or that is a sharp counterexample. All right, now this certain L2 condition on the drift. Here is what I mean by that. We consider time inhomogeneous vector field a priori locally in L2. So when dimension is high, we are pretty far from the LD condition. I will be switching for the illustration purposes. I will be switching from time homogeneous and time inhomogeneous cases from time to time, although there is the time inhomogeneous case, also the next level of difficulty compared to the time homogeneous case. All right, here's the definition. The vector field is called form-bounded. Well, by now, classical definition is called form-bounded if the following Hardy type condition holds. What is written here is an inequality in the sense of quadratic forms. The square of the vector field, this inequality, the quadratic form that corresponds to the square of the vector field is less or equal to than some constant delta times the quadratic Laplace operator plus some extra term, well, g of t, that is priori. So this function in L1. If one is interested in the time homogeneous case, then one can simply take this function to be a constant. And well, to make things more clear, let's say that the constant delta is what is important, really important here. So at first glance, you can ignore the function g. So the constant delta, called the form bound of B with respect to the Laplacian. In the time homogeneous case, one can restate this condition in form of the quadratic, in form of the separator norm inequality. So for some constant lambda, we have this inequality, and again, it expresses the sort of subordination, smallness of the vector field compared to the Laplace operator, or rather the square root of the Laplace operator. The constant delta measures the magnitude of the singularities. As you can see, multiplying a vector field by a constant will change delta. And this is what we expect if we, in a sense, if we go back to the counterexample, let me do it really quickly. Yeah, this counterexample. As you can see, this constant multiple of the vector field is extremely important. And we will see that the C translates directly into delta by Hardy's inequality. So this delta will affect, delta will affect things. By the way, if you have any questions, then please don't hesitate to interrupt me. So to shorten notation, I will be denoting this norm L2, L2 by simply 2 term. It's clear. All right, with this class of vector fields, what are its subclasses? The class, or I should say critical Ladizinskaya procedure class. If one takes q equal to 2, I'm sorry, rather q equals to infinity. So in the time variable, the vector field is bounded. Then one can take r equal to d, and we obtain the class LD. This is the proper subclass of the class F delta, the class of form-bounded vector fields. And moreover, if we continue with the time homogeneous case, B an element of the class LD, the optimal, the maximal possible class at the scale of LP spaces, such a vector field is form-bounded with arbitrarily small form-bound delta. So it's in this sense, this class LD is subcritical, but only in this sense, it's still a pretty large class of the subclass of form-bounded vector fields. Now, if we go further and consider the vector field that we started with constant C normalized as follows to apply Hardy's inequality. Then such a vector field will be form-bounded with exactly this delta. As you can see, the constant C determines delta. And one can continue the class of weakly form-bounded vector fields, or the Campanato-Mori class, or the Chang-Wilson-Wolf class. There are many subclasses. In fact, this problem of verifying which vector fields or which potentials, one can restate given this condition for potentials, which potentials form-bounded, can this condition of form-boundedness be expressed in elementary terms, was a problem that attracted attention of many mathematicians, Wolf and so there is a well-developed machinery that allows to verify form-boundedness. Now, there are, for every epsilon, should change this formulation a little bit, there are vector fields that are not locally in L2 plus epsilon. So this is really an L2 condition. And even though, one cannot, of course, one cannot say that LP with P less than D, the entire class LP is a subclass of F delta, because there are easy counterexamples to any results. Still, there is a huge difference, thanks to this observation, between class LD, the subclass of F delta, and the entire class of form-bounded vector fields. Again, the class of form-bounded vector fields, there's nothing special about P equal to D in a sense. There are vector fields that are not even in L2 plus epsilon. All right, now one again, general comment. Where does it come from, this class of vector fields, form-bounded vector fields? The condition of the form-boundedness with the form-bound delta less than 1 ensures that the quadratic form that corresponds to the operator, the Kolmogorov operator, minus Laplacian plus b times the gradient, that we know corresponds the operator behind the stochastic differential equation that intercells. This quadratic form determines a strongly continuous semigroup in L2. So, in a sense, if we want to have a semigroup in L2, or rather, if we want our SDE to determine a semigroup in L2, then, if we want to use, that's our condition. I will have a lot more to say about that in 15 minutes. Now, its generator is an appropriate operator realization of this formal operator in L2. In general, under such assumptions on B, it's so it's it's all written here. Now, so basically the condition that we're looking at is the condition that, well, is needed to construct an operator in L2. And it's surprising that will take us this far. We will not only construct operator in L2, we will show that this condition, but with delta sufficiently small, allows us to construct a generator in the space of continuous functions, vanishing at infinity, failure generator, and solve stochastic differential equations. All right, now let me state the first result. And in this result, we're really looking at, we're really after delta, well, the critical value of delta, the critical value of the form bound. So I will return to the counterexample of Beck, Fondoli, Gubinelli, Morelli in a moment, but let's state the result. So we have a form bounded vector field. Here, for some reason, it should be time inhomogeneous vector field. I'm sorry, it's P of S, comma XS. Then for every X, there exists a martingale solution to this stochastic differential equation. It's important that we allow any starting point, because if we start removing some starting points, then, well, then we might remove starting points in the singular locus of B, and then it would be less interesting. In particular, if we start removing the starting points, the initial points, that the discussion about the counterexample would not apply. Now, so here's the positive result, and the result that preceded actually the counterexample restated in terms of delta. So I replaced constant C by this normalization. So here's the counterexample. If delta is greater than this constant, then no weak solution with initial point at the origin exists. So we start right in the eye of the storm, in a sense. So you can compare this counterexample, which and the positive result. Well, so far as you can see, we can claim that delta equal to 4 is critical, at least in higher dimensions. And I would like to emphasize that we reach this delta equal to 4, at least in higher dimensions, not just for this particular vector field, but for the entire class of form-bounded vector fields. Now, as you can see, the result is simply the an existence result. There exists a martingale solution. I will continue, we'll talk in a moment about other properties such as uniqueness and failure property. But for now, it's delta equal to 4 that interests us. Yes, and finally, one more remark. When we replace the LD condition by something more general, it's not that we're looking for trying to squeeze out everything from the result and looking for all the small improvements. There are new effects that arise when one transitions from in quotation marks, subcritical class LD bounded vector fields. For example, this effect with delta equal to descent of LP spaces. All right, now about the proof. The proof is the George's method in LP, rather than in the standard for the George's method L2 space, plus a standard tightness argument. Well, I don't have time, unfortunately, to go into details of the George's method. Well, if you know what those of you who are familiar with the George's method, here's the principle, the principal estimate that one obtains, and basically here's the equation. So this estimate, once established, allows to apply standard tightness argument to construct a solution. Now, as you can see, even though we impose an L2 assumption on the drift, and in fact, L2 assumption on the right-hand side, F here can be just a continuous smooth function with compact support. So in the coefficient B, and on the right-hand side, we have functions that can be only in L2, not even in, not even in L2 plus epsilon. still one obtains this inequality, the estimate on the supremum of the solution, and in terms of the right-hand side. So the modification of the DeGeorgis method, standard DeGeorgis method, is almost trivial. One has to multiply. Normally, one is considering such a subsolution, and normally one takes as p equal to 2. So we simply modify the test function, and this is sufficient to reach, replace it by v2 or to reach delta equal to 4. So this is a joint result with Yuri Semyonov, and this is a pioneer of this transition into LP, and gaining a lot from such a transition. So here's another instance where it works perfectly and allows to reach delta equal to 4. Now, so if you allow me, I will continue with the discussion. So again, the modification of the DeGeorgis method is pretty straightforward. Once one knows what one is looking for, the delta equal to 4. DeGeorgis method in L2 was used earlier by Shichen Zheng and Guhuan Zhao, Mikhail Rockner, and other mathematicians, but them above all, with B vector field B in LD, and recently Rockner Zhao with vector field in the weak LD space. So they can also claim that they include this counterexample of Beck, von Dolly, Gubinelli, Morelli, but not with this sharp constant delta equal to 4. So the use of DeGeorgis method in the study of SDEs is not new, and moreover, the for-bounded vector fields, at least in the elliptic case, again in L2, already appeared in the context of DeGeorgis method, so the work of Takunobu-Hara. Now, a few more comments. Speaking of this optimality of delta, Beck, von Dolly, Gubinelli, Morelli mentioned that they require delta to be slightly, at least in lower dimensions, substantially larger than 4, but slightly larger than 4 in higher dimensions. So if actually they show that if delta is strictly greater than 4, this arrives to the origin is positive probability. So already doesn't look like Brownian motion. This result is somewhat similar in the spirit to the classical result of Jerome Goldstein, who considers Schrödinger operator. This is the famous result. This Hardy potential with the form bound, again, form bound historical, that's where the form boundness condition appeared in the study of Schrödinger operator, with delta delta positive, and it's known that if delta is less or equal to 1, then one can construct self-adjoint operator realization of this operator in L2, of this formal operator in L2. But what they've shown that if delta is strictly greater than 1, then all solutions to the corresponding parabolic equations explode instantaneously right after t equal to 0. If one is taken as the initial function that is non-negative and positive somewhere, then all weak solutions will explode. One has to make it slightly more precise. I would have to make it slightly more precise to state it rigorously, but this is what is happening. Now, the counterexample that we consider, again, there is a critical value of delta. And here, what we can be certain of is that the solution, the process, nothing explodes, but the solution no longer looks like Brownian motion, although, nothing explodes, and in fact, one can, it's an interesting question, what is happening when delta greater than 4 if one abandons the SDEs. All right, and the third comment is concerns heat kernel bounds with this, again, with this critical regularity. So if one considers the corresponding operator, then taking this vector field, Hardy type vector field, then the sharp heat kernel estimate was established by Giorgio Mitafune, Sabajima and Chiara Spina this estimate is given here. So this is the heat kernel looks like the Gaussian density times, and we're talking about two-sided bound. So this estimate is sharp times the singular weight. The power of sigma is determined by the constant delta. Okay, hold on a sec. Yeah, okay. Yeah. No, I think there's something that is okay. Yeah, okay, obviously. Yeah, so there is something wrong with the way I stated the result, but they also allow for delta that goes up to 4. And yeah, well, so yeah, ignore this constant. What is important here is that there is an exploding weight. And we are in the situation when, so if you compare this result, this exploding weight, that makes, so the singularity of the vector field makes the standard Gaussian bound invalid. It has to be multiplied by the singular weight. And we are in the situation where this singular vector field, in a sense, makes the operator minus Laplacian, well, the Kolmogorov operator, look no longer like Laplace operator. But the positive result for the SDEs, for the stochastic differential equations, that applies in particular to this vector, shows that the corresponding process still looks like Brownian motion. The solution to the stochastic differential equation exists. So we're in the, well, in the region where what we consider no longer looks like the Laplace operator, but still looks like Brownian motion. Speaking of the difference between two, if one thinks of this, these two objects as two faces of same coin. All right, now let me continue with discussion. Okay, so now we know that delta equal to 4 is critical. So the counterexample of Beck-von-Deuler-Morelli, Gubinelli-Morelli is really sharp counterexample, at least in high dimensions. But what do we gain as delta, the form bound, becomes smaller? Well, even goes to 0, but still, actually no, just fixed but smaller. So this is the second part of my talk. Okay, let me have a look at how much time I have. Okay. So the uniqueness, some uniqueness and failure property. Actually, the results that all the results that I'm stating in this talk are actually proved in reverse order. So the result that about delta equal to 4 is the latest result. Now, let me talk about some earlier results. Now, if B, vector field B, this is a joint, the result is contained in joint papers, Rafael Madou, who already gave a talk at this conference. So if one requires that the form bound is less than d to the power minus 2, so the form bound is smaller. So we forget about delta equal to 4. It's smaller, but still non-zero. Then for every initial point, this stochastic equation has a weak solution that is a unique inappropriate class that increases, that gets larger as delta goes to 0, as one would expect. And this weak solution is determined in the failure process. Actually, to be more precise, it's the other way around. We first construct the corresponding failure evolution family and then show that it admits description as via this stochastic differential equation. Okay. Okay. So, two ingredients of the proof. Well, the failure evolution family that gives weak solutions to the to this partial differential equation. I should mention at this point probably that we can put discontinuous diffusion coefficients here, with not all discontinuous, not all measurable diffusion coefficients, but some that have critical discontinuities still. But I will not be talking about it here. So this failure evolution family, or in the time homogeneous case that would be failure semigroup, is constructed by a certain Moser type iteration procedure that I will describe in a moment. And so the second ingredient of the proof is the following estimates the following regularity estimates on the solution of the inhomogeneous Cashew problem. I already mentioned this inhomogeneous Cashew problem when I was talking about the George's method. Well, one has to be able to solve this equation well, in a good way, obtaining such estimates to be able to conclude, well, to construct weak solutions to the stochastic differential equation. Notice here that although one imposes an L2 condition on the vector field, one can still Q, the power Q, arbitrarily large. Q belongs to this interval as long as delta is sufficiently small. This is where the condition of the delta comes from. We want this interval to be non-empty. But if your delta, the form bound, and this would translate into constant C in front of the vector field considered by Beck, Fondoli, Gubinelli, Morelli, for instance. So if this constant is sufficiently small, as delta goes to 0, this interval expands to infinity. So in particular, one obtains easily, look at the first term, Helder continuity of the solution, even though one imposes an L2 condition on the vector field. Now, this was observed by Kovalenko and Semyonov in the elliptic case. That is, well, for the corresponding elliptic equation, if one is working with the resolvents. Well, if one is working with the resolvents, then this transition to the SDEs becomes harder. But okay, here we're talking about the parabolic case. And the proof of such estimates, which basically goes by differentiating the equation, the PD, without differentiating what cannot be differentiated, without differentiating B. So here it gets trickier, and if one does directly what they did, one arrives at the solution. So problematic terms, but one can find a way out, although at the expense of imposing more restrictive conditions on delta. So for them, for Kovalenko and Semyonov, this delta is can be larger. Right. Now, if I works is one takes the difference between two solutions of the approximation equations. That is, one considers a smooth approximation of the form bound. It's not difficult. Take the difference between the equations that correspond to different approximations of beam. Then one wants to well control this difference, and the only problem is that, of course, this difference it does not satisfy a parabolic equation. It satisfies that is not a difference, but actually gradient of one of the solutions. Now, applying Hildering inequality, and as you can see, the problems here is this gradient. If one can control that, then with appropriate choice of the parameter, one can the left hand side, the right hand side, LP exponents. So one can iterate the norm of the gradient, but one can do that thanks to this estimate. In fact, thanks even to the one can only use the first term to do allows for large delta, as one's written here. So if one can iterate this inequality, then one can simply show that after the difference in terms of the LP norm of this, or even L2 norm of this difference. In L2, one can show rather easily. One can show that UM constitutes a Cashew sequence, and thanks to these iterations, one obtains the supremum norm. One obtains in this way a failure evaluation formula. Now, as is well known, the failure evaluation family determine certain probability measures on the trajectories continues from the right, having limits from the left. And so what we show is that this failure evaluation, this probability measures are actually concentrated on continuous functions and determine, will give us martingale solution to the SDE. So what we do, and this philosophy already appeared in the time homogeneous case in these two earlier papers. So for us, it's a way to characterize, well, this SDE is a way to characterize failure evaluation family. Now, I mentioned this result on the uniqueness in a certain class of weak solutions. In Manafon proved something different. Well, in a sense, sequential uniqueness, or sometimes called stability, meaning that the solutions of failure evaluation family that we construct does not depend on the choice of the approximation of the vector field B. So any weak solution that one can construct via reasonable approximation that does not increase the form bound of B will be unique inside. So we're obtaining the same solution. All right. Now, regarding uniqueness, I will just mention that this result, the uniqueness result is similar. Namely, it's uniqueness satisfy quite natural type estimates. And as I mentioned previously, to construct this failure evaluation family in terms of weak solutions to SDEs, one can only use this term in brown, red. So that's the first time I actually find the use for this term, other than imposing less restrictive conditional delta. So I use this term to prove uniqueness. All right, now the one more remark. One sec. Yeah, it seems like I have 10 minutes. Now this search for the optimal, for the largest possible class of the drifts, vector fields is not over. There is recently result by super class in over here. Here, one can take this Q that determines the behavior in time equal to 1. And the class of form-bounded vector fields requires Q equal to 2. So, in a sense, we need control over the square of the vector field to be able to use quadratic inequality. And here, as you can see, Krylov, at least in the time variable, in the special variables, it's still LP condition, but in the time variable, he went further than that. So this search for the maximal class of admissible drifts is not over. However, I will explain how all these results can be advanced further. Right. So up to now, I was talking about weak solutions, martingale solutions, weak solutions. Well, there is another approach to constructing strong solutions that is based on the stochastic transport equation. Here is this is the equation written here. Well, this circle is the Stratanovich multiplication, or rather Stratanovich integral, once one makes it precise, takes integrals. But one can put the stochastic PDE in this form, in the eta form. And as you can see, this Stratanovich term gives you the something more familiar and the Laplacian here. In particular, now one can see right away that by taking expectation, if one takes expectation, well, the vector field is non-random, of course, so these factors through, the term in the middle disappears because this is a martingale. And one obtains a parabolic, well, the heat equation with respect to this function, the expectation of the unknown of U, the unknown scalar random field. So the stochastic transport equation is really the equation that is, one can say, it is behind the heat equation. Now, there is a link to the SDEs as well, namely, well, here's this link. The solution to the stochastic transport equation can be obtained as a composition of the initial function times the inverse of the stochastic flow for the SDE. So if one can construct the stochastic flow, one can solve the stochastic transport equation. And what Beck, Fondoli, Goubinel, and Morelli did, so the result is not only that counterexample, but they went in the opposite direction. Namely, they explained how solving the stochastic transport equation can be, well, allows to solve the corresponding SDE. And there is obviously an advantage of this point of view because one can use analytic methods to solve stochastic transport equation. So let me just mention briefly that, even the stochastic transport equation, well, it also admits from bounded vector fields. One can prove estimates similar to the ones that I mentioned, namely almost sure Sobolev regularity and Hertz continuity for solutions of the stochastic transport equation. And now, following the idea of Beck, Fondoli, Goubinel, and Morelli, we can construct strong solutions, although at the moment for diffuse initial data. So we would have to, okay, so this X should not be here. Initial data is it's a diffuse initial data, and again, this from boundedness condition appears here as well. And all right, I have.
Sorry, you have
okay, thank you very much.
minutes.
Let me mention, then I will go quickly through the rest of the talk. So I was talking about this from bounded vector fields as really the condition, well, something that allows you to construct the quadratic form, and quadratic form determines the generator of a semigroup. So I was talking about this as really the minimal condition, but it's not true actually. In this construction that I mentioned via the iteration procedure, this construction is difficult because one has to work with Cashew sequence. One doesn't have any really candidate for the limit. We cannot simply guess the answer. But what if we can guess the limit? Maybe we would have to have some representation for that, and I will explain what I mean by that in a moment. But by doing that, and actually, so by basically one can do several things at the same time. So one can consider vector fields that are locally in L1, and here I'm talking about time homogeneous case. Although we have some advances in the time inhomogeneous case. So that is a priori only in L1 locally, and one can replace the form boundedness condition by the following condition. It's like one is taking square roots everywhere. So we call it weakly, this vector field is called weakly form bounded. Standard form bounded vector fields are weakly form bounded, but the opposite direction is not true. There are weakly form bounded vector fields that are not in L1 plus epsilon. So we approach L1 locally. By the way, speaking of this L1 condition, of course, one can pose this problem, this question, pose in the SDEs for vector fields that are measure valued or even distributional. And we have results for measure valued vector fields, and some results, but only at the level of heat kernel bounds for the distribution vector fields. Now, I also have non-local results, but related to this question. So it's not limited to diffusion processes. Now, once one abandons the form-bounded vector fields, well, one sees that the standard methods of perturbation theory are no longer applicable. For instance, the form method. This is something that one wants to do, for instance, to apply Lumière-Phillips theorem and so on. But one cannot do it. One can do it with the form-bounded vector fields because then one can control the square root of the vector field. But here it can be done. Vector field can be L1 block only. So still we can well basically do everything that we did already by guessing the resolvent. So that's the third and the last theorem. Again, B is a weakly form-bounded vector field, and now I made well, as you can see, now there is a type. So the vector field has to be time homogeneous here. So even with going beyond the form-bounded, to construct failure semigroup and solve SDEs, and the crucial observation is that one can guess the resolvent in LP in this form. So basically, just a few more remarks and that's it. So these operators QP, GP, and TP, well, this will be bounded operators in LP. The question how to transition from an L2 condition, and one needs L2 condition to be able to apply all this machinery, all these subclasses. How to transition to LP for large P? Well, I guess I will. Well, that's the tricky part, and I guess I'll skip it. But let me just say that by guessing this resolvent, and formally what is written here is the Neumann series. If one expands, if one uses the geometric series to expand this operator. Now, one obtains immediately just from guessing the resolvent regularity results. You see there is this regularizing factor here, Bessel potential, and there is this regularizing factor there. So when P is large, one can apply Sobolev embedding theorem to get to C infinity, and this allows to construct the failure generator. Okay, I guess I will. Yeah. Okay. Well, even the construction is not so trivial, but anyway, let me stop here. Thank you very much.
Okay. Thank you very much for the talk. For very heavily loaded talk, and floor is open for discussion. Are there any questions, comments?
May I ask Damir to make kind of not a table but a summary of behavior of solution for such thing?
Okay.
No. No, sorry. It's wonderful to have.
Well, well, yes, actually, we're writing in a survey, so it will be put somewhere in one place. But actually, yes, you know what when I was preparing the slides, I thought that no way I will be able to cover 40 slides. But actually, I did. Well, okay, maybe it was too fast, but yeah. So yeah, we're working on that. It will be put in one form, one place.
So can you give a short summary?
Okay. Yes. Sorry. Yeah. So basically, there are three theorems here. The third theorem. Let me start from the end because that's how it's historically appeared. B is in weakly form-bounded vector fields. Delta is very, very small in a sense. Mm-hmm. So here is the delta, and there is the constant MD at the bottom. Delta is very small, but still finite, or non-zero, I should say. Now, if one continue with that, then one arrives to this result, theorem 2. Here we can treat time inhomogeneous vector fields. Delta can be larger.
So result is that there is a unique weak solution. Okay. Mm-hmm.
Yes, but and moreover,
something about the behavior.
Well, this is a regularity result, so it's not just I wouldn't put so much emphasis even on uniqueness because what is really important here is that we have failure process. Okay. Because having a failure process, that we have strong mark of so on. So Yeah, but speaking of regularity, we can actually could continue and complement all that with Gaussian and non-Gaussian bounds in the heat kernel. So under the same assumptions, or rather sometimes assuming imposing conditions on the divergence. But yeah, and in the fifth, well, to answer your question completely, and here is the first theorem, which is actually the last theorem, that says that if we require that only delta is less than 4, and we know that beyond that there is a counterexample, then we can only claim for now that there is a martingale solution. No results in uniqueness of failure property at the moment. Yeah.
So we're making our delta bigger.
Yes, exactly. Yes, the bigger delta, the less you know. The smaller delta, the more you know.
Mm-hmm.
Yes.
Mm-hmm. Okay, thank you.
Mm-hmm. Thanks.
I have a question. What happens when the noise disappears? In a sense, can we put here coefficient mu near to the Brownian motion and try to consider limit mu to 0? Or
no, that is a great question. So one arrives at the stochastic, well, one arrives at the transport equation, and yeah, that I asked this question myself as well. So it's not. Yeah, not much is known actually at the moment, but this is a very natural and very good question. So, in particular, this delta less than 4 actually, yeah. So it may actually a way to go beyond delta equal to 4. It might be exactly that what you're saying to happen with the transport equation. Because one can well, in a sense, trade in huge delta for this small coefficient. So we can view it as a disappearance of the Brownian motion, as you mentioned. So, but I don't have anything concrete to say at the moment.
Okay, thank you.
And also small, I don't know, remark, that there are some results of Dian Palagachev, Daria Pushkinskaya, Alexander Nazarov about solving PDEs with measurable coefficients.
Mm-hmm.
So very, very weak assumption.
Okay. Yeah, so okay, I will look it up. But Nazarov, he has a series of papers, in particular one with Ralsov, when they go beyond, they consider B and LP P less than D. So there are rather, well, one cannot prove much regularity there, but one can still use the George's method and obtain some results. So in this case, in this sense, this class, of course, does not cover what they proved. So there are
no. So the main guy is Dian Palagachev in this theory. In this series of papers. So I don't know how much papers there are, but yeah.
Okay. Yeah, I will look it up. Thanks.
Mm-hmm.
Mm-hmm.
Okay. Are there any further questions? If not, okay. Thanks, the speaker again.
Thank you.
I believe that there is a technical, digital coffee break and again photo session. So we'll have to smile for the next 15 minutes, according to Ivan. Okay. Let's think.
Thank you, Damir. As everything start and finish in time, we have 4 more minutes for discussions of that talk. And only after that, I will announce the coffee break.
Okay.
So everyone has